Hello everyone, welcome back to Data Programming 1. I hope everyone is doing well. This is lecture number 26 and would have taken place on Friday, March 27th. Thank you all for your feedback about the class so far in the video lectures. I value that greatly, and if you have more feedback, please use our feedback form on the webpage to let me know how I'm doing, things I can do better. I did want to address one of the comments that I got, and that was, please make everything bigger so I can read it on my mobile device. Absolutely, I can definitely make everything bigger. And I just wanted to talk a little bit about the best way to use this lecture, the video lecture format, and watching it on a mobile device is probably not the best way. And if you have an alternative during the pandemic, I recommend using a computer. So, in fact, one of the claims I made in class was that watching me lecture about programming is probably the worst way to learn programming. But I'm going to revise that. I think watching a video lecture on a mobile device is probably even worse. But I do my best. I get paid to lecture. I get paid to do this. And I want to make it the best possible experience for you guys. So I believe firmly that the best way to actually learn to program is to do it yourself. So one of the advantages of a video lecture is you guys can pause me. You can go and try things out. And in today's lecture, I'm going to point out several places where I do want you to pause the video and go try things out. Today we're going to be writing code that handles errors, so we're going to be writing code with errors in it. And the best way to learn about these things is to go do it yourself, to experiment, and then come back with questions that you have. Ask them on Piazza, or you can send me an email, or come to our virtual office hours. All right. So today's learning objectives. We're talking about errors today. And one of the things we're going to do is actually learn how to make our code crash even more. If you guys have been attending my lectures or watched the first video, you know that I write code with mistakes in it all the time. My code crashes all the time. I don't really need help making my code crash more if you think about it. But hopefully along the way, when we learn more about errors, we'll learn to write code that's better and crashes less. But first, why would we want our code to crash even more? That sounds crazy, right? Well, crashing is not actually the worst thing that can happen to a programmer. Suppose you work for a company that designs engineering software, and that engineering software is used to design airplane wings. And suppose that your code has a bug in it, a giant red bug that actually doesn't produce the right answer. It gives an answer, it doesn't crash, but it's the wrong answer. And as a result, the airplane wings aren't strong enough, and the airplane crashes. Okay, it would be so much better if the code crashed instead when we realized that there was a semantic error. So if we can make that happen, that would be great. Okay, so if we can turn a semantic error into a runtime error, we can improve our code. And then along the idea of how to crash less, do you know that every time your Python crashes, it generates that error report? It tells you that there was a type error in line 5, and that line 5 is in a function that was called from line 17. Well, that error report is part of what's called an exception, and it's generated by Python every time it crashes. But there are situations where we might expect the code to crash. If we're taking input from a user, and we're dividing by whatever input they give us, if they give us a 0, we're not going to be able to divide by 0, and Python's going to crash. But if we expect that this might happen, we can test for that and catch exceptions when they happen with the try catch and then deal with them. So our code can actually continue on without crashing at those places where we would expect it to. Okay guys, let's take a quick look at our example code for this lecture. Today we'll be using Pizza Analyzer for all of the examples for the rest of the lecture. So at this point, I'd like everyone to go download this code, open it up in Python, and follow along with me. To get there, we're going to go over to the class webpage where it's Friday, March 27th, right here. And this one right here, this link to the lecture labeled code, follow that, click the link. This opens up our GitHub page, and the Pizza Analyzer program is right here, pizza.py. Same as with all the rest of the projects, you can right-click on raw, save link as, and download this code. All right, I've already done that. I've got it open and idle, ready for us to go, and I've got PowerShell ready to run the code. Let's start with that one. So I've typed in Python pizza.py, so that'll run this code. And the first thing we see is that it's asking us to enter the diameter of a pizza in inches and the number of slices. So let's start out with a medium pizza, 14 inches, and we'll cut it into 8 slices. All right. Now it's reporting that this pizza has a radius of 7 inches. We're cutting it into 8 slices, and it gives us the area of each slice, 19.24225500323748. All right, that's a lot of decimal places. I'll take care of that in a second. Okay, let's take a look at the code, though. So first thing we do over here in the actual code, we're going to import math so that we can call math.py. In the very first function here, pizza size, this takes one parameter, the radius, and it's just returning the squared radius times pi, so pi r squared. It's computing the area of a circle. Probably could have come up with a better name, but it is computing the area of a pizza, so I guess it makes sense. The next function we have is slice size. This is taking the radius and the slice count. First thing it does is it's going to call pizza size and compute the total area of the pizza. And then it's going to take that total area, divide it by the number of slices, and return the area per slice. Okay, so we've got those two functions. And then if we take a look at main, we've got a loop here. It's going to run this 10 times. And there's two pieces to it. The first one, we're going to get input. And then the second one, we're actually just going to do the analysis and print out the results. Okay, so let's take a look at this input. The first thing we're doing is using the input function to get the user to enter the number of slices and the diameter. And that's getting stored in a variable called args. If you don't remember the return type of input, pause the video, go print out args, print out the type of args. You'll learn more by doing it yourself than waiting for me to tell you that it's a string. All right, it's a string. I just gave away the answer. So input always returns a string. So over here, I've got 14 and 8 as a string. The next thing we're going to do is we're going to take that and call the split command or split function on a string. Args is a string, and we're going to split it using the comma. So it's going to go through the string and break it into a list where each of the elements in the list is a string. If you don't remember how this works, pause the video, go add another line right here that says print args, and see what it looks like. You'll get a list back. Okay. Next up, we're going to do some type conversion. So start with the innermost part of this parentheses. We're taking arg0. That's going to be the first element in the list over here, the 14. It's going to call strip on it. If you don't remember, the strip command removes all of the leading and trailing white spaces. So if I had a bunch of spaces in there, it's going to get rid of those so they won't get caught up and may generate errors when I convert the type to a float. So this first number, I could have a size pizza that's like 14.5. It's going to get converted to a floating point number. It's asked for the diameter right there, and we're dividing by 2 to get the radius. Okay, then finally we're taking the second argument, again, calling strip on it to remove any leading or trailing white spaces, and then we're converting that into an integer. Very good. And finally, we go down here, we're calling our slice size function to get the size of each slice, and then we're going to print this out. So, for example, we're going to use this string here that's being printed out, and we're going to call format on it. Just a quick reminder of what format does. It's going to take each of these pairs of curly braces and replace those with the data from one of these variables. So, and it's positional, so the first pair of curly braces is replaced with the first variable. The second pair of curly braces is replaced with the second variable, and so on. The third one is replaced with the third. Okay, real quick. I didn't like all those decimal places. So these format strings also take arguments. So I can put in the command to print this out as a floating point number. That's the kind with a decimal place. And I'm going to tell it to give me 2 decimal places. All right. Okay, at this point, what I'd like you guys to do is pause the video and go through and see how many different ways you can cause any sort of problem by just giving this program bad input or inappropriate input, and just see if you can break it, see if you can generate things that go wrong. I've got 9 items on my list. So I'm going to go grab Coke. When I come right back, then we'll go through the list and see how well yours matches up to mine. All right, everybody, welcome back. So for the first thing that I want to demonstrate that could be possibly a real problem for this code, let's go ahead and run it real quick. What if I were to enter 0 for the number of slices? So let's have a perfectly reasonable sized small pizza. We will cut that into 0 pieces. And that instantly is going to crash for us. It's giving us a division by 0 error. And that's coming in right up here. As soon as I grab the total size using the diameter, and then I'm dividing by the slice count. No one can divide by 0. That's not a thing. And so it gives us a division by 0 error. Okay, let's try another example. Clear, bring it back. Okay, number of slices. Let's have ASDF slices and diameter and JKL semicolon slices. When we do something like this, I've just added some completely nonsense, inappropriate input, and this is also going to crash for us. It's giving us a value error message, and it's saying it cannot convert string to a float. And the first time it's trying to do that right here as our float conversion, it's taking the first argument, which is ASDF, and removes the trailing leading white spaces and tries to convert that into a number, but it's not a number, so it crashes. Okay, next let's try, what if we leave out the comma? So what if we put in 4-inch diameter pizza with about 4 slices? What do you guys think is going to happen here? It's going to crash, but where is it going to crash? All right, I'm pushing enter. There it ran. Hopefully I gave you enough time to think about that. So it tells us it's giving us a value error, can't convert string to float, and it's actually crashing not on this line right here. Split works just fine, even though there's no comma. It's just returning a list that only has one element in it, and that's 4 space 4, so 3 characters in a string. And it can't convert that 4 space 4, right there, that string, into a float. It's not completely composed of decimals or in a single decimal point. Okay, so next up, let's try just entering one thing. So what if we just have an 8-inch diameter pizza and no slices? This is going to crash too. And it's going to crash for a different reason. This is giving us an index error this time. And so we get the input. We entered the number 8. That's great. It splits it. Totally works. There's no comma, so we get a list with exactly one thing in it. That one thing is valid, so args of 0 is can easily be converted to a float. But then there is no args 1. The list isn't big enough. So we're getting this list index out of range error. Okay. Next up, what if we were to, whoops, totally missed, put in 3 things. Let's have a 6-inch diameter pizza. We'll cut that into half, and we'll give it an extra number. What do you guys think will happen here? Okay, totally fine. There's nothing wrong. This is a potential semantic error, because it kind of indicates that the user didn't understand what the program really needed, and they gave it an extra input. So it's giving a perfectly reasonable answer back, 14.14. It's using the 6 and the 2 to get that. It completely ignored the 8. Args bracket 2 bracket is never used anywhere. But we don't actually check for this and verify that the user actually understands what's going on. Okay. Let's see. What if we were to put in negative numbers? So let's see here. What if we put in of a 14-inch pizza, and we'll cut that into -6 slices. All right. Is this going to crash? Will it work? Is it the right answer? Let's take a look. It didn't crash. Instead, it tells us we have radius of 7, slice area -25.66 square inches. Oh wow, negative pizza. Negative pizza. Is there anything more sad than negative pizza? All right, so hopefully a reasonable human is going to recognize that there's no such thing as negative pizza and understand that they did something wrong. But Python has no idea. It's never eaten pizza before and doesn't know that it can't be negative. So this is one of the things that's generating an error that is sliding through, a semantic error. And what we'd really like to be able to do is convert stuff like this into runtime errors so that the program actually crashes and lets us know there's something wrong rather than letting this kind of thing slide through. Okay, let's try the other negative number. So right now we have let's have a negative 14-inch diameter pizza. We'll cut that into 8 slices. This also doesn't crash. It's giving us a negative radius for the pizza, 8 slices, but this is insidious. This is bad. It's actually giving us a perfectly reasonable looking answer for the area of a slice, even though we put in input that's clearly bad. So this is something we definitely want to catch. And this is the scariest one of all of them. This is the kind of thing that causes your airplane to crash because the engineer gets an answer back and says, yeah, that looks reasonable. Let's make the wing that thick. And some 19.24 millimeter thick airplane wing might not be enough. Okay, next up. So we tried 0 slices. What if we put in 0 diameter? 0 diameter, and we'll have 4 slices. What's this going to do? Radius is still 0, slice area of 0. I guess this kind of makes sense. If we have a 0 diameter pizza, no matter how many slices we cut it into, they're all going to be 0. We might want to check for that. It doesn't make a lot of sense for our program to do that, but nothing wrong with it there. I guess the same deal with if we have 100 billion inch cross diameter pizza, and we'll cut that into 2 slices. That should be enough to keep me full for a while. It's still going to work. It's a huge number. I guess there's no real upper limit on the size that you could make a pizza. I'm not sure what we should do there. I'd say we'll just leave that one alone for right now. Okay, let's see what else we got. Let me check my list. Okay, so what if we were to take a 14.5 inch diameter pizza and cut that into 2.5 slices? Not really sure how you do that with a regular pizza cutter, but let's try it out. Another error. Okay, so what's this one say? This is a value error, invalid literal for int typecasting. So this is coming from this line right here, where I'm converting the argument 1, or my 2.5, into an integer. So it can't do that as directly. Taking a string to an integer, if it's going to lose information, Python won't let us do that. If we did want to do this, we could actually go ahead and turn the int into a float first, like this, and then turn the floating point number, turn the string into a floating point number. So that would be a 2.5, and then float numbers can be cast into integers, but they just are rounded down and they lose information when that happens. I'm going to take this back out for a sec. Okay, next up, what's the last one? Oh, that's 9 already. We're good. So we really want to make sure that if our code is trying to work with invalid input or is producing an answer that we as a human know to be wrong, for example, if it's producing negative pizza, we want to be able to catch this. And to do this, Python gives us a method called the assert statement that takes care of this for us. It's really easy to write. It's just the keyword assert followed by a Boolean expression. So anything that we could have put in an if statement, if some Boolean expression, if x is less than 3, if pizza is less than 0, we can call that right here with the assert statement. And all this is going to do is cause the program to crash. So, and this is good because if we have a semantic error, something nonsensical that is still working, this is going to be really hard to find. And it allows us to turn those semantic errors into runtime errors, which are much easier to catch and debug. So let's take a look at what happens when we actually run a statement like this. If it's true, absolutely nothing happens. So the Boolean expression is true. If the pizza area is positive, it's just going to keep right on going. If we've asserted that if pizza less than 0, and the Boolean statement is false, it's going to crash. And this is going to generate a crash report just like any other time I've written code that has bugs in it. Note down here at the bottom, the type of this error is assertion error, And just like the rest of the crash reports, it tells us that this occurred in line 4 in pizza size, assert radius greater than 0. That was called from pizza.py in line 8, just like the rest of them. And a heads up, it's possible to disable assertions in your code. They do take just a tiny fraction of a second to evaluate one Boolean expression to decide whether to crash or not. But some people disable them to improve performance. So you cannot rely on assertions being in your code when other people run it. And I highly recommend that you leave them enabled. Okay, let's head back over to the code, add some of these things to our pizza analyzer, and give them a try. All right, how about right here in slice size where I'm taking the radius and the slice count. We'll put this as close to the point where we're using it as possible. So let's first assert that the radius is greater than 0. If that's true, it should continue right on with no trouble. And then let's also assert that slice count is also greater than 0. All right, save that. Let's head back over here and run this. Let's just make sure it's still working. So if we have a pizza with a diameter of 2, we cut it into exactly one slice. Diameter 2 means a radius of 1. 3.14 times 1 is 3.14. One slice means we should get 3.14. We do. Looks like it's still working. Okay, now let's try some of these things that we know were bad. Especially, let's start with the minus 4-inch diameter pizza. This is the one that before worked just fine, gave us a perfectly reasonable answer because the first thing we did was square minus 4, became a positive number, and carried on without any trouble. So we'll get a negative 4-inch diameter pizza into 4 slices. And now we see this crashes. So right here in this line, assert radius greater than 0 was false. It's generated this assertion error, and we see the rest of the error log there. Okay, I'm going to try this one more time with, we'll use a positive error. We'll have a 9-inch pizza, and we'll cut this into, how about 0 slices? This was a problem last time, and again, still a problem right here, but now we're getting an assertion error because we are checking for this right here in the assert slice count greater than 0. Right there. Okay, let's head back over to PowerPoint for part 2 of the lecture and talk about what if we want to keep the code running, even if there's an error? For example, if I write some code that grades student homework and I'm using assertions, when an assertion is false, the code crashes. So if I'm using that to check and see if you got question 1 right, and you didn't, and the code crashes, it's not going to continue on and grade the rest of questions 2 through 35. So what we really want is a way to be able to deal with this and continue going. So Python gives us the try except block as a way to check out some code, to try it and see if it generates any errors. And if it does, then we can run the except code and fix those or deal with them somehow. So suppose I make the really poor decision of calling flaky function. This is some code that is known to crash. One of the ways I can deal with this is I can put this into a try except block. So in the try block, this can be more than one line here. In this case, I only have just the one flaky function. If this generates any errors, then this code in the except block runs. And this again can be many lines. It's a block. In this case, it's just going to print out an error message. So this lets us deal with the errors rather than just having the code crash. A couple of things to note. Try and except blocks come in pairs. They're always in pairs. The errors that are generated, runtime errors, are known as exceptions. And part of the exception is that error message. They have a type. So when Python tries to run the code in the try block, if there's an error or an exception, then it jumps down and runs the except block instead of crashing. And this is known as catching the exception. If nothing goes wrong, then the except block doesn't run at all, and the code just continues from that point on. Okay, so let's jump back into the pizza code and add some of these. So bring that up. All right, so there's two main places where things can go wrong. And when we get all this input from the user, in the grab input section right here, the user could enter gibberish or some invalid data that doesn't work. That's one place. And the other place where things can go wrong is in the analysis. If they do enter valid numbers, but suppose it's a negative number, right up here, we've got assert statements that are causing the code to crash should they put in something negative. So I'm going to go ahead and add try and accept blocks right here. Move that over to catch these and deal with them. So right here, if anything goes wrong when we enter the input, we should let the user know that their input is bad. Bad input. And we'll be polite. Please try again. Okay, excellent. Now, if they do enter bad input, we don't want to actually call the analysis and let that crash. So this is actually running in a for loop. So instead of just ending the program, we will just continue. That will skip this block that does the analysis and let the user try putting more input in. Okay, and then the second place, in the pizza analysis, this could have math problems. So let's put this section of the code also in a try except block. And in this case, we'll let the user know that there is a math error, analysis error. And again, please try again. All right, and in this case, there's no need to for the continue because it's the very last thing. It's already going to go back up to the top of the loop. Yeah, this is looking good to me. Let's head over and try this out. Clear. We'll run Python at pizza. Okay, let's just make sure this still works. So if I have a 9-inch pizza, whoops, bad input. Please try again. I was going to try some correct input. Here, let me do 9-inch pizza cut in 2 slices. Looks like it's working. Okay, excellent. Now let's try some of those things that generated bad input before. So for example, if I just put in one number, like the number 9, I do get that bad input. Please try again. So what's happening right here, this was the error where I took the input as a string, it split it, gave me a list with exactly one thing. This line worked fine. It used the first argument. This line only was the out of bounds, not enough arguments in the list, something like that. And so this caused the code to crash. So instead of crashing now, it's gone down and run the accept block. Bad input, please try again. And then jumped up and it's letting us try again. Okay, let's try another one of these. Let's see. Last time I had ASDF. No, I used the JKL last time. Whatever. In this case, it's trying to turn this string into a float. That's a type error. Can't convert string to float. And again, bad input, please try again. It's jumped down and run this piece of code in the accept block. And let's see, finally we had 8 and 2.5. It can't convert a string with 2.5 in it into an integer right there. So again, please try again. And finally, let's try the divide by 0 one. So a 9-inch pizza, cut into 0 slices. In this case, all the input processing was just fine. We get down here, we call slice size. First thing it does is check to see if the radius, and then right here, slice count is greater than 0. It's not, it's equal to 0. So this assert would cause the program to crash normally, or in this case, generate an exception, which we then catch instead of just crashing. In this case, it prints analysis error. Please try again. Okay, excellent. So let's head back over here. We'll kill this. We'll kill it. Kill it. Actually, so every time I type Control-C, there it is again. What's happening is it's actually too good at catching errors, and it thinks my Control-C is a bad input and is refusing to die. That's actually why when I wrote this code, I'm using a for loop right here so that when it gets to 10, it will stop no matter what. If I were to use an infinite loop, which I normally would for something like this, I'd have to actually close out my terminal and start again. So this version is a little bit too aggressive. It's catching absolutely every single possible kind of exception, including my Control-C. and refusing to die. So we're going to need to be a little more specific about the kinds of things that can go wrong and how to catch just the things that can go wrong and let something like Control-C, killing the program, go through, because we do want that to happen. So let's head back over to PowerPoint. All right, control flow. So exceptions are going to be things that actually disrupt the normal control flow that we'll see when we're writing code. Remember at the very beginning of the course, we talked about how the general rules, we run each line exactly once, and we do the lines in order. And then things like loops let us repeat lines, conditional statements let us skip lines. Well, exceptions are also going to break up that control flow. So, got an example here. Let me just pull this up in Python Tutor so we can walk through this one line at a time. Let's see here. There it is. So I've got the same code here in Python Tutor. This is just gonna, here, in a try block, we're gonna, let me click next, print out the inverse of 2. 1 divided by 2 is 0.5, then 1 divided by 1 is 1.0, and then 1 divided by 0 is an error. Down here at the bottom, we see we get 0 division error, division by 0. This isn't gonna work, but it's okay. This is in a try block. So the moment this happens, it doesn't run this line, it doesn't run that line, it's going to skip directly to the except block. And there it is, the red arrow moved, and then it's going to print out, that's all folks. So this is what I mean by an exception to normal control flow. Instead of executing each line in order one at a time, as soon as it generated that error when the program would have crashed right there at the 1 divided by 0, it skipped ahead all the way down to the except block and printed out that's all folks. Those lines did not run. Okay, I've got another example here. And these examples are available on the web page in that code folder, the same one you downloaded the pizza folder from. Let me just paste this in. So you can go and grab these. All right, let's take a look at this one. So I'm defining 3 functions here, buggy, G, and F. Then we begin by calling F. So this is another example about control flow, and it's about who takes responsibility for errors and where they're dealt with. Okay, so the first thing that happens is we're going to call F. And in a try block, let's see, right there. Oh, first thing we do is call F. Then in a try block, we're going to print out, hey, this is F, let's call G. Then we're going to call G. We jump into there. G is going to say, here we are right before buggy. Now we're going to call some code that has bugs in it. So we jump up into buggy. Buggy is very honest. It's about to fail. And then we're going to divide by 0. And this is going to generate an error. There's the 0 division error. From here, it's going to skip the rest of this. And it's going to first say, does buggy know how to deal with this? It's not in a try except block right here. It doesn't. So it's going to jump from buggy over here in my frame up to the next level and see if G knows how to deal with it. So return value none, it skipped down to the end of that. Here's where it was called from. Does G know how to deal with it? It is not in a try except block here either. So it jumps down to the end of G, return value none, and goes back up to F. Here's where it was called from. It's going to see that it's in a try block right now, and it's going to skip down to the except. So it did not print this line. The G return normally, that never prints. Instead, we're down here in the except block, and now it's going to print that didn't go so well because of that divide by 0. So in this case, it starts at the very bottom of the stack and works its way back up to find the closest place where there was something that could deal with the exception. If we were to put a try block a little closer, for example, let's put one around the actual statement that causes the problem. We'll try this, and then accept, and we can print out excuse me. Whoops. Wrong screen. That didn't work. And then it's going to continue. All right, so let's walk through this version now. Head back over to first. Define the 3 functions. We call F. That calls G. That calls buggy. And we get to right here, buggy about to fail. It tries this line tries to divide by 0. That doesn't work. Instead, it prints out that didn't work. And in this case, Buggy caught the error and dealt with it. And now what's going to continue on? Error has been dealt with, so it prints out oops. And then we're going to jump back up into G. G actually finishes just fine because the exception has already been caught. The error has been dealt with. Continues on. When G returns, it goes back up and prints G returned normally inside of F. It skips the except block here, and we're all done. Okay, so what if we want to know the reason that we had an error, or the reason that an exception was generated? Right now, we've been working with version 1 here, where we have a try statement, we have a block of code that's going to generate an error, or create an exception, and then in our accept block, we've been handling it. This except statement with just the colon is going to catch absolutely every single possible kind of error, including that Control-C keyboard interrupt error that was preventing us from exiting the code. So we'd like to upgrade this and be a little more specific and learn a little bit more about what's going on. So to do this, we can actually upgrade this except line and create an exception object. So this here, everything in Python is an object. So lists are objects, integers are objects, strings are objects, functions are objects, and exceptions are also objects. So this exception object contains all of the data we need to know about what went wrong. And this particular exception object E is of type exception. We have lots of choices for what type of exception, and the exception version is very general. We've seen a bunch of these already. Every time our program crashes, that error message tells us what went wrong. It could be an index error, a value error, a type error, a name error, lots of choices. But every single one of those exception objects has the ability to turn into a string and be printed out. This is just going to be a description of why this failed. So let's go to the code and actually add in a line like this and see what's going on. So we have two try except blocks here. This first one was dealing with things that go wrong with the input. So let's catch these exception as E. And then let's go ahead and print that out just like we were just seeing. So we have bad input. Rather than try again, let's let them know what's wrong with it. So we'll turn E into a string and get that printed out. And also while we're right here, let's also print out the reason we had a problem. Cause of error. And then this will be type of the exception. All right, and same thing down here for the other except the math problems. We have exception as E, colon, and then we'll also print out just copy it from right here. I guess it's not really bad input anymore. This still should say analysis error. Analysis error. And then we'll also copy this line and print out the type of it. There we go. Cause of error, type E. Save that, head over to PowerShell, we'll run this. And now let's try some of these things that gave us errors before. So number of slices, diameter, 44 inches. I'm going to leave off the other one. This gave us an index error before. And so we see bad input. Typo here. I forgot my quote, comma. I'm just printing out string E. It's not actually doing what I wanted. I've done it twice. Hold on. I make mistakes all the time, guys. Everybody knows that. All right, let's get this fixed. All right, number of slices, 44. All right, here we go. Bad input. List index is out of range. Check this out. A very useful error message. Tells me that right here, when I'm accessing args1, it's not actually there. Arg1 not big enough. And this is going to be an index error exception. All right, let's try another one. Let's see, what else didn't work? Oh, yeah. We put in characters. Here we go. Bad input. Could not convert string to float. Here is that error message associated with the exception. So when I converted this exception into a string, That's the error message that was printed out. And the type of this error message, right there, cause of error, is of class value error. So it's trying to take one type of value and turn it into another. All right, one last one. Let's do the 9-inch pizza divided into 0 slices. Okay, now this particular error, there's no message right here. And it's that's right. It's of type assertion error. We actually generated this ourselves. So when we went up here, this line right here, line 8, asserts that slice count is greater than 0. And should it, in fact, in this case, it's exactly 0. And because it's not greater than 0, this is causing the program to crash or create an exception of type assertion error. And that is caught down here. But this isn't really very specific. It doesn't give us an error message, something useful. So let's go ahead and upgrade this right now. So the assert statement lets us actually add a comment right here. So let's say slice count is less than or equal to 0. Make sure I did this right. So 9-inch pizza, 0 slices. And there we go. Now we have an error message associated with this particular assertion error. Slice count less than or equal to 0. Okay, and in a few minutes, I'm going to be talking about how to change this from assertion error to something more specific. You know, we've got all kinds of options for different types of exceptions. We saw index error, we saw name error, we saw value error, divide by 0 error. Assertion is quite general and it's not specific to this type. So we'll see how to change that in a minute. I'm going to head back over to PowerPoint. There we go. And now, what if we only want to catch certain kinds of exceptions? We wanted to, for example, that keyboard input. We definitely did not want the keyboard interrupt to stop us from exiting and killing the code when I was typing Control-C. So the version 2, this is what we were just working with. I'm trying flaky function that creates an exception because there's some kind of bug in the code. I'm catching that exception as E and printing it out. Now, if I want to be more specific, I can go ahead and replace that word exception with a tuple. So I've got my smooth parentheses here, and then I've just got a list of every possible kind of thing that I really do care to catch. So exception is very general, and I only want to catch specific things. I definitely don't want to catch name error. A name error means that I have typed the name of a variable wrong. That's a problem with my code, and I want that one. Hold on. Yeah, demo time. Let me show you what I mean. So for example, right here, I'm getting input from the user, and suppose my variable args here has a typo. You can't have semicolons in the name. There we go. There, everybody see the typo? So if I were to save this and then run it, and enter number of slices, let's have a perfectly valid 9-inch diameter pizza cut into 8 slices. I'm getting a bad input error. Now this isn't actually bad input, it's perfectly good, but it says local variable args referenced before assignment, class unbound local error. And that's because I have a typo in my code. So highly undesirable to catch this and try and deal with it as bad input. What I really want to do is use, let me fix my error, something a little more specific than exception because I don't want to catch this unbound local error. So as a general rule, I want to be very specific when I catch exceptions. I want to list the exact ones that I really want to be able to catch. I want to make sure that I'm not catching typos in variable names. And the other part of this is I want to make sure that I always print something out. A lot of times people will use exceptions to gloss over bad input errors, but then never tell the users there's something wrong. Just try again. Let's take a look at the exception hierarchy. Oh, that's much too small. 1 second. Okay, here we go. So we have lots and lots and lots of different kinds of exceptions. Let me scroll down and just show you. Nobody has these memorized. You look them up when you need to. So in version 1, we just had except : That's this catching a base exception. That's every possible thing that might go wrong, including the keyboard interrupt that's right there. When we started version 2, we were using exception as E. That's going to catch everything in the list in this hierarchy below that. So still lots and lots and lots of things, including things like name errors and unbound local error, which is a type of name error. That's the one we saw when I had the typo in my code. We don't really want that. It'd be much better to catch specific things like this, zero division error or arithmetic error. So let's pop back into PowerPoint and finish up by talking about what if we want to produce a specific kind of error, not just that assert. Even if assert lets us have a message, it's still not a specific type of error that's built in. For example, that division by 0. Right now, it's generating an assertion error with the black arrow when it's technically division by 0. It might be a much better choice to choose to create a zero division error exception. So let's talk about how to do that. So this is what we have right now, version 1. Quick and dirty. We're just asserting that radius is greater than or equal to 0. If it's not, then it creates an exception, an assertion error, and stops running code and goes down to find the nearest except clause that can deal with it. And if there isn't one, it crashes. Okay, version 2 here is a little more informative and a little more specific, and specific is always good. So in this case, I'm replacing assert radius greater than or equal to 0, that second line up there, with 2 lines. The first one is a conditional statement. So if, in this case, I need to raise the exception if it's true. So I'm switching it. So if radius is less than or equal to 0, if that's true, it's bad. And in this case, we want to create a new exception. I'm creating an arithmetic error here and just letting the user know with this message that the number of slices is less than or equal to 0. So that's bad. And then in order to tell Python that this is an exception and it needs to go deal with it, I need the keyword raise. So the full command is raise, name of the exception, arithmetic error in this case, number of slices less than or equal to 0. This is the phrase, the command that says skip everything, don't do anything else in the code until you find an except clause that can go deal with this. So let's go back over to Python and actually try some of these things out. So how about right here? Instead of asserting that the radius is greater than 0, let's replace this with something more specific. So in this case, if the radius is less than or equal to 0, it needs to be true before I take action. So if the radius is less than or equal to 0, that's bad, and I want to do something. We're going to create an exception. Exception, call it negative radius as the message. And then in order to tell Python that it needs to do something, it needs to take some action, it needs to skip the rest of this code right here and travel all the way down until it can deal with the exception right here in this except clause. I need the keyword raise. And in fact, exception probably isn't the best choice. That's very general. Let's go pick something else. I'm trying to find something that deals with if the radius is too small, if radius is inappropriate. So let's take a look at my list of choices. Oh, how about arithmetic error? That's perfect. Already highlighted. So instead of exception, let's go with arithmetic error. All right. Save that. Let me just run this and demonstrate that this works. Okay, number of slices, radius. Oh, diameter first. So we'll have a diameter of negative 12 inches, and we'll cut that into 6 slices. Remember when we first started working with this would have given us a positive answer and looked just fine. Now, we've got to the point where there's an analysis error, and the message is negative radius, and the cause of the error is no longer assertion error, but now arithmetic error. So very specific, very good upgrade in this case. All right, let me just wrap up with a quick summary. I've got a summary slide in PowerPoint. There we go. So we've talked about 2 things. First, assertions. Assertions are a way to take code that has a problem. I can put in something that I know as a human to be true and enforce it to crash. Or in this case, create an exception. And it's much, much better to crash than to produce the wrong answer. And the second thing we talked about was exceptions. We talked about how to catch them and how to deal with them with try except clauses, how to use them to get useful information out of the program, and then how to create our very own exceptions with Raise, where we can choose the specific type of exception. And as a final note, just to review, be specific when you're trying to catch particular kinds of exceptions, and definitely tell the user there was an error. Definitely print something out. Okay, have a great day, everybody. And if you have any feedback about this particular lecture, if anything, if you have any questions, please take them to Piazza, or you can come to office hours. And have a great evening.